In this video, I'll go through how current and potential difference behave in parallel circuits. I'll derive some of these results and finally I will apply it to an exam question. So to do this, I've got two parallel circuits and I'm going to go straight into the first rule, and that's that current splits at a junction and is shared proportionally. Now let's look at what I mean by that. So I'm going to look at the first circuit. The longest terminal is always positive, the shortest one is negative. Conventional current flows from positive to negative. It will move around the circuit until it reaches the junction. Now some of the current will go through this loop, we'll call it I1. Some of the current will go through this loop, we'll call it I2. Now how large I1 is depends on how large this resistance is compared to this resistance. Now let's do the same for the second circuit. Again, longest terminal is positive, shortest one is negative. Draw in our conventional current. Gets to a junction. Now depending on how large the resistance in loop 1 is compared to the resistance in loop 2 determines how large I1 and I2 are. Now we can write this mathematically because the total current must be made up of I1 and I2. So we can say that the total current is equal to the current in loop 1 plus the current in loop 2, and then if we had a loop 3 we would add that on as well. And let's be clear, this is only in parallel. And I'm going to call this equation 5. Now let's go on to the second rule for potential difference. Potential difference is the same across parallel loops. Now it's really important that I've said parallel loops and I've not said across components in parallel. This is because we need to calculate the potential difference in each loop, not across individual components. So let's first identify what I mean by loops. So the shortest path I can take from the cell back to the cell, that will be loop 1. The next shortest path I can take from the cell back to the cell, that's going to be loop 2. So just so I don't get my colours mixed up, I'm just going to draw it there. So loop 2. Let's do the same for the second circuit. So we've got the shortest path from the cell back to the cell is loop 1. And then the next shortest path from the cell back to the cell is loop 2. So then just so I don't get my colours mixed up, I'm only going to draw it there. So I've got loop 2. So for example, let's look back at circuit 1. If I have 10 volts supplied by the battery, loop 1 will also get 10 volts. But depending on the size of the resistor, we might have 7 volts across this one and 3 volts across this one. Loop 2 also receives 10 volts, but again, depending on the size of the resistor, we might get 4 volts across this one and 6 volts across this one. And then the same thing for the second circuit. If we have a 10 volt cell, the first loop must also receive 10 volts, but we've only got one resistor, so that's going to be 10 volts. The second loop must also receive 10 volts. So we could have 6 volts across this resistor and 4 volts across this resistor. Mathematically, we can write this as the total potential difference is the same as the potential difference in loop 1, is the same as the potential difference in loop 2, and if we had a third loop, loop 3. And I'll call that equation 6. Now I'm going to go through the mathematical derivation of why current splits at a junction. So let's go back up to rule 1 and see that current, if we remember from video 1, is the rate of flow of charge. So it shouldn't come as a surprise that rule 1 is a consequence of the conservation of charge. And this is exactly what you need to write to get 1 mark in the exam. You have to say it's due to the conservation of charge. I'm going to draw a simple circuit to help me explain this. So we draw 1 parallel loop. Then I'm going to draw another parallel loop. And then longest terminal is positive, shortest one's negative. So we get our conventional current flowing in this direction. Once it gets to a junction, depending on how large this resistance is compared to this resistance, it's going to split into I1 and I2. And the conservation of charge says that the charge entering a junction must be the same as the charge leaving a junction. So we can say the total charge is equal to the charge in loop 1 plus the charge in loop 2. But current is the rate of flow of charge, which tells us that charge is current times time. Now if I sub this formula into my formula above for each term, I get that I total times time is the current in loop 1 times time plus the current in loop 2 times time. Now the next point is really important, and it's what gets you the mark in the exam, and that's to say measurements are taken over the same time t. The same time t. Now this gets you 1 mark. And what this means is that because all the times are the same, we can just cancel through by t. So we get that the total current is equal to the current in loop 1 plus the current in loop 2. Here is an exam question on exactly what we have covered. If you'd like the mark scheme or you have any questions, please feel free to message me. I've left my email in the comments below.